In this problem, we have a chandelier that is supported by several ropes, and we are given that if the ropes are of the same kind and they will fail if the tension force reaches 400 pounds, we need to determine the maximum weight the chandelier can have without causing any of the ropes to break. So normally we would be given the weight of the object and we need to determine the tension force developed in the cables supporting it. But in this case, it's the other way around. We're given the maximum tension force the cable, the ropes can bear, and we need to find the weight instead. So it's a reversed process. So there are different ways to approach this problem. I'm going to show my way, which I believe is the most effective way. So I will start with the free body diagram of ring D. So in this case, based on the analysis, the detailed analysis that I gave for problem 2, we already know that here, this force, which is the tension force in this cable, simply equals to the weight of the chandelier. It is not the same as the weight of the chandelier, but in magnitude, it equals to the weight of the chandelier. And also, it is subjected to the tension force Tc and also the tension force Tb. And that completes the free body diagram of ring at D. So in this case, you can see that we have 3 unknowns, and this is a 2D particle equilibrium problem. We can only write 2 scalar equations that will enable us to solve for only 2 unknowns. However, I'm going to treat W as if it's known. So I'm going to treat W as a parameter and solve for TB and TC in expressions of W. So again, I'm going to apply my Newton's first law. Resultant force along the x direction equals to, so this is my positive x direction, and that equals to negative TB. The directions are given. This is a 45-degree angle, so that is cosine 45 degree plus positive TC. This angle is the same as this, 30 degree times cosine 30 equals to 0. And then resultant force along the y direction, this is positive, equals to TB times sine 45 degree plus TC times sine 30 degree minus W equals to 0. So even though I cannot solve for TB and TC explicitly, I can solve both of them as functions of W. Okay, so I'm just gonna do a little sketchy calculation here. So I have square root of 2 over 2 times TB plus square root of 3 over 2 times TC equals to 0, and then I have positive square root of 2 TB and then plus 1/2 TC minus W equals to 0. So from here, if I add these 2 equations together, then TB cancel out. So I will have square root of 3 plus 1 over 2 times TC equals to, if I move W to the right hand side, W. So from here, TC equals to W divided by square root of 3 plus 1 over 2. So as you can see, I can solve for TC as a function of W, and TC solved this way equals to 0.732 W. And then I can substitute that into the first equation, because from the first equation, TB equals to square root of 3 times TC divided by square root of 2. So I can solve for TB as well. And TB equals to 0.897 W. So, of course, I understand that my job is not done, but I am going to use my TB and TC solution here into my second free body diagram of ring B, and then solve for the other tension forces also as functions of W. So next, I draw a free body diagram of ring B. So because of action and reaction, inside this cable, the force TB or TD is the same as TB. Therefore, that's simply 0.897 W, the same as this one. And also, I have this force right here in this cable. It's called BC. And lastly, I have this force right here. It's called a TAB. So again, I can set up my Newton's first law equations. Resultant force along the x direction equals to negative. This angle right here is 30 degree. TAB times cosine 30 degree plus TBC, and then plus the component, x component of this force, which is 0.897 W times cosine 45 degree, and that equals to 0. And then resultant force along the y direction equals to positive TAB times sine 30 degree plus TBC doesn't have any vertical component, but so actually it should be negative. But this force right here has a vertical component that is negative 0.897 W times sine 45 degree equals to 0. So as you can see from the second equation, I can already solve for TAB, which equals to 0.897 W times sine 45 degree over sine 30 degree. So from here, again, TAB is a function of W, 1.268 W. And if I substitute that into the first equation, I can solve for TBC as well, which equals to 0.464 W. So let me summarize what I've done. Even though I don't know what W is, I have solved for all the tension forces as functions of W. So if you count this cable as well, that's fine. In this cable, the tension force is simply W. And then in this cable, that is my TC here, the tension force is 0.732 W. In this cable, that's my TB here, the tension force is 0.897 W. And in this cable, that's my TBC, the tension force is 0.464 W. And lastly, in this cable, that's my TAB, the tension force is 1.268 W. So doesn't matter what W is, these tension forces developed in these cables will change proportionally. So these ratios will always be the same. Therefore, in any circumstances, we can tell that the tension force in cable AB is always the maximum, because this coefficient is the maximum out of all the coefficients. Therefore, if any cable or any rope is going to break first, then rope AB must be that rope. Rope AB must break first because it's always bearing the largest amount of tension force. And we know from the problem statement that the rope will fail if the tension force reaches 400 pounds. Therefore, since cable or rope AB controls therefore we can set TAB, which equals to 1.268 W, to be that maximum tension force, which is 400 pounds. Therefore, from there, we can solve for the maximum allowable weight force, which is 315 pounds. It's actually the maximum failing weight force. And that solves this problem.